I'm also recording in this class, so I always like to just give you a heads up. So first of all, what's going on in the schedule? You had a quiz last class. Quizzes, remember, are small grades, so they don't totally ruin your grade if you didn't do a great job on it, but it is an indicator of what you still need to study. A lot of times the quizzes are these basic essential skills in chemistry that you need to have, such as drawing a Lewis structure, doing electron configurations, creating ionic compound formulas, and in this one it is completing and balancing the major types of chemical reactions. That's the major idea for a lot of this unit. And so if you didn't do well, remember there is tutoring after school today. You can check to see what you got right, what you got wrong, what strategies you need to employ as you're studying for the unit exam that's next week. On that note, you will have a unit exam next week on this unit, which is on chemical reactions, the deep dive into chemical reactions. Because the quiz was all written, the exam itself is going to be mainly multiple choice. I'll give you the spread next week, but it'll be largely multiple choice. I'm just giving you that heads up. So make sure you are practicing using the Bower quizzes for practice to make sure that you're getting the ideas of how you're going to be assessed. What types of questions you could have, of course, include making the correct products, determining if something is soluble or not, determining if a reaction happens, and then what we have coming up this week. We have 2 more lessons this week. They're all about a specific type of reaction called redox reactions. The major classification of reactions that's really important in whatever future study that you do in an AICE course, whether it's chemistry or not. So we're going to go ahead and we're going to study that this week. On Monday and Wednesday, we've got 2 lessons. You'll notice there's a handout today because the main thing we're going to learn how to do today is how to assign oxidation numbers. And we'll get a quick glimpse at what redox is, and then we'll do more with redox next class period. Then on Friday, we have another lab, actually. So there'll be a lab on Friday, another lab. If you didn't yet turn in your lab report from the last one, make sure to turn that in for your group ASAP. Because I did put those grades in. I checked them over, I believe, when I checked over the test. And there'll be another lab again on this Friday. I was going to put your test next week on Tuesday, but there's honor roll, and typically at this school that means more than half the class is gone for most of the class period. So that means that will be an extra review day for my B days, and you're going to have your test next week on Thursday. So the test for Unit 5 will be next week on Thursday. Mark your calendars for that. We'll be reviewing then, because we have a lab on Friday, we'll be reviewing on Tuesday, and for the first part of class on Thursday. All right, so that's that. Those are the schedule things. Let's go ahead and get started with what we're doing today. So last but not least, next week on Thursday, you'll also be having a binder check. I will be checking your notes, so make sure you are taking good notes throughout the class period and filling in any notes you don't already have. Today we're doing Unit 5, Lesson 5 out of 6, and we're doing redox reactions, Day 1. There'll be 2 days in this lesson. I'm giving you a little bit of time. Take out your notes, write down the lesson title. We'll get started in about 30 seconds. As I'm waiting, there is another important announcement for the school that I do want to remind you of. There is 2 drills today. One of them is going to be a fire drill or an evacuate drill. That is taking place during 4th period. So they're doing it during 4th period, close to the beginning of 4th period. And the other note is that there is going to be a lockdown drill during lunch. This is something that is mandated by district for all schools. So it's not, we didn't have a choice in it, but what you do need to pay attention to is if you are in the lunchroom, when the lockdown drill sounds, you need to go to the auditorium. And if you're outside, when the lockdown drill sounds, you need to go to building 700. So my suggestion is when you get to lunch, if you're going to be eating outside, look for building 700 so you know where to go. It's not going to be at the beginning of lunch, it's going to be more closer to the end of lunch when you have the lockdown drill, but it will be during lunch today. So mentally prepare yourself for that. That's taking place during 4th period. Well, you have more more than, like, lunch is supposed to be 30 minutes and you get 40. So yeah, it'll take like 5 to 7 minutes of your lunch. The last part. So eat your lunch at the beginning of lunch is my suggestion. And all schools have to do this. So it's not just us. My husband's a teacher at another school and they have the same exact drill today during lunch. So unit 5, lesson 5, redox reaction, day 1. What? That's when it usually is. Unit 5, lesson 5, redox reactions, day 1. Here we go. So what we have to do today, and you don't have to write this down, but last night I was thinking, what are the things we need to get through? We need to be able to assign oxidation numbers, which is what you have that sheet for, which I'll be talking about in a little bit. We need to define what is oxidation reduction and redox reactions. You'll be writing the definitions for those today. And then by the end of the class period, we're going to learn how to determine in a chemical reaction what has been oxidized and what has been reduced in a chemical reaction. That's what we're going to be learning about today. So you don't have to write this down. This is just like to track what we need to do. You will want a periodic table out again, or have knowledge of how to get charges on your periodic table and standard states on your periodic table. So the one that has your standard states, the one that has your charges, you may want to have that out handy and available because we're going to need that again today. Go ahead and start with this. What is a redox reaction? So what is redox? What does that even mean? Some of the classic reactions we've been studying are always redox. Some of the classic reactions we've been studying are never redox. And some of the classic reactions we've been studying are sometimes redox. So what is a redox reaction? And the lab we're going to be doing on Friday is all about redox reactions specifically. It has something to do with oxidation. That's true. Redox. Something that has to do with something called reductions and something called oxidation. Well, what does that even mean? In biology, you've seen oxidations. Something called oxidative phosphorylation. That is oxidation. The electron transport chain. That is redox. Cellular respiration is redox. Photosynthesis is redox. So many of our biological reactions are actually redox reactions. What in the world is redox? So we're going to go ahead and define that very shortly. I just wanted to give you some time to write it. I'm moving forward in about 10 seconds. The definition is coming up first. So I've mentioned it in passing a few times, that one of the reasons we study electrons so much is because electrons are what are transferred in chemical reactions. And so a redox reaction is actually any chemical reaction where a transfer of electrons takes place between two elements, meaning one element gains electrons and one element loses electrons. So make sure you're writing down the definition. It turns out many chemical reactions are redox reactions. A lot of them are, and a lot of very important ones are redox. Some of them are not. There are other types of chemical reactions that can happen, but most chemical reactions are actually redox, meaning that a transfer of electrons has in fact taken place. So make sure you're writing the definition. You do need the definition. Are you taking it? You're writing that? Are you taking it? And so what we're going to do on the next slide is we're going to define what does this process look like at its most basic level. We'll revisit some ideas we started talking about in Unit 3. Giving a little bit more time, about 20 more seconds. If you didn't get it down, just take a picture. We are moving forward shortly. where transfer of electrons takes place. Where's that? Where have we heard of transfer of electrons before? We've definitely heard that. Something we talked about a lot in Unit 3. When we form ionic compounds, what happens is one element loses electrons and another one gains electrons. That's where we've heard transfer of electrons before. So although not always involving ionic compounds, it will often involve ionic compounds. And so let's review of determining when to use ionic charges, because this is going to become important today. So you're going to want to write this down and leave this blank because I'm about to go over what you need to know. So write review of determining when to use ionic charges, and then I have a couple of examples. Mg when it forms into a compound, MgO, and then oxygen when it forms into the compound MgO. That's not what I'm asking. So what I am asking is, when do I use ionic compounds for an element, ionic charges for an element? When do we consult the periodic table to know sodium is +1, oxygen is -2, sulfur is -2, fluorine is -1? When do we do that? And why do we do that? Well, let's review. If we have the element magnesium, how many valence electrons does magnesium have? It has 2, which we would represent as 2 dots, right? Magnesium has 2 valence electrons. Magnesium has a low electronegativity, yes, I'm bringing back words from the past, and a low ionization energy. What does that mean about magnesium? Would it like to gain or give away electrons? It will give away electrons. But it can only give away the amount of electrons that it has. So when magnesium goes into the compound MgO, it does this because it gives away 2 electrons. And you end up with this, Mg2+, and those 2 electrons are off to the side. Well, where did they go? If we're forming the compound MgO, then they went to oxygen, if that makes sense. So if you start with oxygen, oxygen has how many valence electrons? 6. It has 6. And how many valence electrons does oxygen want to have? Wants to have 8. And is oxygen in the business of giving away electrons or receiving them? And why? Receiving. Why does oxygen want to receive electrons again?
Because it wants to reach the octet.
To reach the octet rule. But magnesium loses electrons to reach the octet rule. So why does oxygen gain? Whereas magnesium loses?
Because it'll be
Yes.
easier for you.
Because it has a high electronegativity. And we're going to say for magnesium because it has a low electronegativity, which I use EF when I don't want to write a lot.
Mg and O, like, it's the alliance they reach the octet.
Yeah, they form their bond with each other. One has to give away 2 electrons, and those 2 electrons go to oxygen. And so we say that 2 electrons are going to oxygen, and you end up with oxygen that instead of having 6 valence electrons, it has 8 valence electrons. And if it has 2 more electrons than it had before, what is its ionic charge? If it gains 2 electrons, electrons are negative. It has a -2 charge, or a 2- charge, right?
Yeah.
Those charges we consult from the periodic table, we consult for a reason. It has to do with the octet rule and whether an element gains or loses electrons to become like its nearest noble gas. I'm bringing back this information because it's going to be really important in determining oxidation numbers in a little while and understanding why. So ionic charges are used when form an ionic compound, right? When you have an element in an ionic compound or an ion in aqueous solution. We learned that a couple of class periods ago. If I have NaClAq, that means that when I throw salt and water, I have Na plus 1 and Cl minus 1. That's the other time we use ionic charges. Yes, go ahead. All right, so I'm giving you a little bit of time to write this down. This is a reminder, but it's going to be, like I said, really important because we're about to learn how to assign oxidation numbers to elements, either in their standard state or in compounds. And if you understand electronegativity, there's really not a lot to memorize here. But if you don't understand electronegativity, well, then you got a lot of rules to memorize. So this is where understanding earlier in the class is going to come into play. In what type of reaction would magnesium and oxygen combine to become magnesium oxide? You remember? If I'm saying Mg goes to MgO, and if I wrote it correctly, O2 goes to MgO, what am I describing here? I'm describing a synthesis, right? It's not balanced at the moment, but this is synthesis. So in a synthesis reaction of this type, where I'm forming an ionic compound, one element has to give away electrons and another one has to gain electrons. And so we would classify that as redox because a transfer of electrons has taken place. That's the idea behind today's lesson. If a transfer of electrons takes place between two elements, we have redox. We're going to learn how to track what the charges are. We're going to call those oxidation numbers. You'll see why very shortly. And then we're going to learn how to determine what's been reduced and what's been oxidized in a redox reaction. So the first thing we're going to move to now is something called oxidation numbers. And you're going to want to write this down. The definition is important because it's going to help us understanding what's going on. And you should probably also write what's in here, so I'll give you some time because that's an example of some oxidation numbers. So we classify an oxidation number as a positive or negative number, just like a charge, assigned to an atom to tell us how oxidized or how reduced it is. If I have a cation or an anion, it will be the exact same as the cation's ionic charge and the anion's ionic charge. So oxidation numbers actually broaden the scope from ionic compounds to also include covalent compounds. So for ionic compounds, and I'm just going to write this on the bottom and you should add what I add, oxidation numbers are the charges. And for covalent compounds, which we're now going to expand to, oxidation numbers are unofficial or theoretical charges. You should write that down. So I'll give you some time because there's the definition, the example of how to write them, and what I've added, which is really important. In an ionic compound, we're literally going to be looking for the charge, and that is the oxidation number. So if sodium has a +1 charge, in a compound, it also has a +1 oxidation number. For covalent compounds, the idea to track what's happening with the electrons is to assign unofficial or theoretical charges. Because in covalent compounds, electrons are not transferred actually, they're shared. And so it's saying for the oxidation number, if an element were to hog the electrons or were to gain electrons, which element would it be? And so you're going to have a bunch of rules that describe how to do this, but really just a couple ideas that you need to remember. I'm giving you some time. Write it down. And then we're going to get to practice questions on determining oxidation numbers shortly after we go through the rules. I'm tracking to see if you're still writing. Just make sure to put your pencil down. I know that I gave a lot here, so when you're done, put your pencil down so I know to continue, when to continue. You'll notice where the oxidation numbers are placed is right above the element in question. And you'll see the example they use is water, hydrogen having a +1 oxidation number, and oxygen having a -2. Those charges should look familiar as they are the same ones we were looking at before. Hydrogen is always +1, oxygen is always -2. That sounds somewhere else in the school. I believe the next slide will be the one that has the handout. When you get to the slide that says rules for assigning oxidation numbers, you don't have to write all that down. When there's something that has a lot of writing, I typically print it out in advance, so I did. I see at this time most of you are done writing. So I'm going to go ahead and give you a 20-second heads up that I am about to move forward to explain how to assign oxidation numbers. So if you do need to take a picture, please make sure to do so shortly. All right. Moving forward now. Yep, here we go. So on this handout that I passed you while you were working on the bell work, you should write Unit 5, Lesson 5, so you know where this belongs. Remember, I will be checking for your handouts if you do have them. If you lost them, you can rewrite them into your notes because I do post the presentations for the lessons after class along with the recording after school, after I teach the last class period. So, let's go through the rules. Rules for oxidation numbers assignment. The first rule, the oxidation number of a monatomic ion is equal to the magnitude. What's the word magnitude mean? How big the number is, right? So the magnitude and the sign of its ionic charge. So that means that if you have an ion, trust what they tell you. Trust. If it says Mg2+, as an example, what's the oxidation number of Mg2+? trust what they gave you is the ionic charge. It sounds silly to say that, but a lot of students get messed up here. So if you are given an ion, that is the oxidation number. Its charge is the oxidation number. That's rule 1. But so far that makes sense, right?
Yeah.
All right, rule 2, all about hydrogen. So rule 2 is all about hydrogen. Remember, we always have these rules, and then we got to discuss hydrogen. Hydrogen is almost always positive 1. Uh-oh. Almost always. It's usually plus 1, but there is an exception. The exception is if you have a compound where hydrogens combine with a metal. The example being NaH. What would be the charge of hydrogen when combined with a metal? The oxidation number. So typically, for example, if you've got HF, hydrogen would be plus 1 where fluorine would be minus 1, right? That would be typical. So what happens if we've got a compound with a metal? What would hydrogen's oxidation number or charge now become? So what you have to remember, welcome back, is in an ionic compound, and you have to remember it this way, or else nothing's gonna matter. The first element has to be positive, and the second element has to be, it always is cation first, and then anion second. So this is actually being described to you the way that it's telling you what's gonna happen. Sodium is then plus 1, and what's hydrogen gotta be? Minus 1. So this is the exception. When hydrogen is with a metal, instead of having a positive 1 oxidation number, it will have a negative 1 oxidation number. Well, what's that? What do you think? Why can't it be hydrogen plus 1 sodium minus 1? Why it can't be like that? Why not H plus 1 and A minus 1? Why can't we do that? Why can't we do that? Why not? The answer will always lie in electronegativity. Hydrogen is more electronegative than Na. Because non-metals are more electronegative than metals is the idea. So that's why. So that's why that can't be. But it's typically going to be written to you in such a way that you'll see if you got a compound, remember the cation comes first and the anion comes second. We organize compounds from lowest electronegativity element typically to highest electronegativity for a reason, so that we communicate effectively what's going on. And so you would see it as NaH when hydrogen doesn't have the charge it usually should have. You would see the H in the back, usually. With organic being another exception to that, but we won't talk about it. Number 3. The oxidation number of oxygen in a compound. So this is the next rule. Highlight oxygen. Is usually -2, which hopefully makes sense. There's actually 2 exceptions. It gives you 1 here, but there's 2. I'll bring up both of them. Why is oxygen usually -2? How many electrons you need to go to your nearest noble gas. So then, what would be the situations where it's an exception? We actually memorized this polyatomic ion at one point, peroxide. It's O2, 2 minus. The only way to get O2, 2 minus is for oxygen to be -1. That's the only way. And we'll go over this later. But in peroxide, oxygen is -1. There is one more exception. The other exception is if you have oxygen with fluorine. Why would that be an exception? Right. Fluorine takes the negative charge no matter what, right? Takes negative oxidation number or charge no matter what. element, it's going to steal electrons from anything, and if it was going to steal electrons from something in this covalent compound, it would steal them from oxygen. And so in OF2, knowing that fluorine is -1, what would oxygen then have to be? Think about it. +2. It would have to be +2, right? So that would be the oxidation number of oxygen in OF2. Those are the two exceptions for oxygen. In everything else, oxygen is -2, except for these two very specific exceptions. When oxygen is with the most electronegative element, and when oxygen is in that specific polyatomic ion. Only that one. So 99% of situations, oxygen will be -2 in a compound. All right, number 4. This is the one y'all gonna be like upset about, but you know what? Oh well. Memorize your standard states. I told you this 100 times by this point. The oxidation number of any element in the element standard state is, guess what? 0. That means if you don't know your standard states, you're not going to be able to predict that. This, for example, means that if I see Mg solid, what's the oxidation number of magnesium here? 0. If I see N2 gas, what's the oxidation number of nitrogen in its uncombined state with another element? 0. And what does this really mean? What does an oxidation number of 0 mean? Part of 0, oxidation number of 0. What's being described? Okay. What does an oxidation number of 0 actually mean? What is an oxidation number of -1? What does that mean about the electrons? Because that's what we're going to care about, right? Not that it has no electrons. It has all of its regular electrons.
Oh, doesn't need any.
It has not transferred. No, it's not about what it needs. It's about what it has. It has not transferred electrons. This is just magnesium the way it naturally is as an atom. And this is just nitrogen the way that it naturally is. It has not given away electrons. It has not received electrons. Does that make sense? So the oxidation number means hasn't given or received electrons from anything. So that's why we say when it's in its standard state, that's just the element as it exists. It hasn't transferred electrons. It just has what it has. And that's why it's 0. You're going to have to look out for elements that are by themselves to always have an oxidation number of 0. 5. And so rules 5 and 6 is where most of our work is going to be. And this is where your critical thinking skills are going to come into play. A little bit of possible math. For any neutral compound, so underline neutral, neutral compound. Neutral means charge of, overall charge of 0. Charges canceled. And here's the math. The sum of your oxidation numbers, that means you're going to have to add. When you add up all your oxidation numbers in your compound, all of your additions have to equal 0 because it's neutral. That's rule 5. So that's a math rule. We will have to do some math here. And then finally, and this will be the most difficult one, we will be looking at it today, for a polyatomic, of course. Well, I said most difficult and then I said polyatomic ion. For a polyatomic ion, the sum of your oxidation numbers in a polyatomic ion must equal the overall charge of that polyatomic ion. And so we'll be going over how to look at that, how to analyze that very shortly. So, I have a question for you. Will this be given to you on the test next week? Absolutely not. This is actually supposed to be intuitive. Cambridge would not give this to you, absolutely not, on a Cambridge exam. This is something that via electronegativity and just understanding charge balancing that you need to be able to pick up. So this is helpful for you for the bell works and for your homework, and we'll be looking at it today, but you actually need to either memorize the rules or intuitively understand what's going on with the electron transfer. One of the two. For next week, Thursday, for the test. And we'll have time, like I said, there's 2 more lessons and then it's all practice until next week, Thursday. So let's go over, starting with, me solving them. How do we figure out the oxidation number in each of the following scenarios? So here we go. What is the oxidation number of each kind of atom in the following examples? You need to write these down. We're going to go through a lot of examples, like 6 or 8 of them, just to make sure you've seen each situation. What is the oxidation number for each kind of atom in the following? What do we mean by each kind of atom? There's another way I could have said that. So atoms of each element. So each specific element we will need to provide the oxidation number for. Yes. Yes, you may. Somebody's out right now. You have to wait till Rachel comes back. What is the oxidation number for each element? And we're looking at A being Br2L. First of all, is Br2L an element or a compound? Element or compound, Br2? One capital letter. This is an element, right? So
Zero.
element or compound should be your first thing you're thinking. Element. That should be something, you don't have to write this down. That's something you should be able to analyze in your head. Well, the next question for the element. Is it an ion or is it in its standard state? So that's really the only two options in the rules we have for elements. Is it an ion or is it in its standard state? When we're analyzing this, these are the two questions we should ask ourselves. Well, is Br2 liquid? Are they presenting you with an ion? You see a charge there? No. So you won't write -1 as an answer, right? Is Br2L in its standard state? Any element in its standard state, the answer is 0. The answer to this question is 0. Oxidation number of bromine is 0, meaning it has not gained electrons, it has not lost electrons, it just has the amount of electrons it has. It has not given or transferred electrons to any other element, officially or unofficially. Let's take a look at B. Element or compound? Right. Element or compound? Compound. So how will we get the oxidation number of each element in this compound? Remember, rule 5 talks about compounds. If the compound is neutral, you're going to add all the oxidation numbers to equal 0. What does that actually mean here? How would we get the oxidation number of aluminium? We're going to look at our periodic table. Aluminium is +3. What is bromine? -1. Do those oxidation numbers add up to 0?
No.
Are you sure? You have 1 aluminum plus 3 bromines equals to 0. If you're unsure, make a little equation. Don't you have 1 aluminum and 3 bromines? Do you agree? 1 aluminum, because these are our amounts down here. 1 aluminum plus 3 bromine equals 0. What is the number for aluminium again from the periodic table? What's positive 3 times 1? 3. And then what about bromine? It's 3 times what? -1. So what is +3 and 3 times -1 is -3. Does that equal to 0? Yeah, that works. So the answer is aluminum is +3 and bromine is -1. Meaning that each aluminium loses 3 electrons and each bromine gains 1. you have a simple ionic compound like this, you don't have to justify the work. But when it gets more complicated, you will want to. Like when you have a polyatomic ion. So this is just you checking to make sure the overall charges work out and become 0. Aluminum should be +3, bromine should be -1. End of this. Questions about how we got aluminum being +3? Bromine being -1, are we good with that? We're moving on to the next example then. As usual, what I like to do is start with what is considered to be the easier examples, and then we move on to more complex. So, CO2. CO2. Element or compound? Not polyatomic. Where's the polyatomic ion there? There's not even an ion there. That's carbon dioxide. Compound. Just a covalent compound, right? Welcome back. Alberto? All right. If we have a compound, the rule we have to follow is that all of the oxidation numbers have to add up to 0. But how will we know what is carbon and what is oxygen? Is there a rule that can tell us one of them? On your list of rules? Remember that compounds always go, and you may want to write this down, from least electronegative to most electronegative. So out of carbon and oxygen, which of these two elements is the most electronegative? Carbon or oxygen? The one closest to fluorine, or the one written second, which is oxygen. So what that actually means is the most electronegative element should keep its charge, because it's the greediest, it's going to get electrons, right? So the most electronegative element keeps its negative charge that it desires. So out of carbon and oxygen, they're both non-metals, but they can't both have negative charges, because overall the whole thing has to add up to 0. And if everything is negative, it won't add up to 0. It don't work. So out of carbon and oxygen, which one's going to get the negative charge? Oxygen. So here's the way to reason it out. We know oxygen's going to be -2. And we know, and what rule tells us this? This is rule 3. But you should know that based on electronegativity as well. What's the other rule we need to use? We have a compound. All oxidation numbers have to add up to what?
0.
So pay careful attention. There's 2 ways to do this, and you're going to decide which one you prefer. The first one, so method 1, is to set up an equation. And so for those of you that like to visually see everything, this may be your preferred method. And so what do I mean by an equation? You're going to write the amount of each atom and what its oxidation number is. So how many carbons do you have? 1. So the way you set it up is like this. 1C plus how many oxygens? Plus 2 oxygen. So we do capital O for oxygen. And what does that equal? 0, because it's a neutral compound. So that's set up an equation. Then what you're going to do is plug in any known oxidation numbers. So the next thing you would do is you would plug in what number for what element. What do we know the oxidation number of? We said we knew it for oxygen, right? So plug in -2 for oxygen. And so going back to our equation, we would now have 1 carbon plus 2 times negative 2 equals 0. And so what would we do next? Solve for carbon, because that's the one we don't know. We know oxygen, we don't know carbon. So then we would solve for carbon in the final step. So you would do C, what's 2 minus 2? Negative 4 equal to 0. And now solve for carbon, what would you do? And yes, this is algebra, because you will either have to employ algebra or use algebraic thinking to solve.
4 plus negative 4. And then
Just
4
plus 4.
plus 0.
And so then carbon would equal positive 4. And so your answer is carbon is, because there's 2 methods that you can use. But this is your answer. That's how you would describe your answer. Carbon is positive 4, oxygen is minus 2. Now I told you there were 2 ways to do this. One of them was to set up an equation. Method 2 is to logic this out yourself. Meaning, looking back at CO2 again, take a look at oxygen. Each oxygen is negative 2. You would multiply negative 2 times 2 oxygens. What number is that? Negative 4. You know the whole thing has to equal to 0. So if all the oxygens are negative 4, then what do all the carbons have to be? The opposite side. So that's the logic part that you would have to figure out that, oh, this has to be positive 4. And then you would split that between however many carbons you have, which is 1. And that tells us that carbon is positive 4. And so you can logic it out. There are 2 methods to solve. You can either set up an equation or you can figure it out. It's up to you. Cambridge doesn't mind either, as long as you can explain how you did it. So that's example 3. Remember carbon was in group 14. It could have a +4 or -4 charge. It turns out that it just depends on what carbon is connected to. It's connected to oxygen. Oxygen's more electronegative, so it has to take the positive number. If it was connected to a metal, it would have to take then a negative number. And so it just really depends on electronegativity. We're going to look at example D. I'm leaving this up for just a little while longer if you're writing down the method. I'm going to actually delete this so that I have space for the next one. So I'm deleting this very shortly. If you need to take a picture. 5, 4, 3, 2, 1. Try to give myself a little bit more space in the next class. Let's look at SO4 2 minus. All right, SO4 2 minus for D. What do we do here? First of all, what is that? What is SO4 minus 2? Oh, polyatomic, right? It's a polyatomic ion. And so what that means is really the way to understand it is it's SO4 and it all has -2, right? That means instead of everything adding up to equal 0, we follow rule 6, which is everything adds up to equal the charge of the polyatomic ion, which is -2. And so that's the first thing, is understanding we're going to apply rule 6. All the numbers have to add up to -2. Now, out of sulfur and oxygen, the next thing you have to ask yourself is, out of those 2 elements, which of them do you know the oxidation number of automatically? Oxygen. The more electronegative element, and if there's a specific role for oxygen, oxygen is almost always -2. So then how will we solve for sulfur? Knowing that oxygen has to be -2, that I believe is rule 3, this means we have to solve for sulfur. And you'll always have in compounds or polyatomic ions 1 that you have to solve for. And so now we're either going to use method 1 or we're going to use method 2. I'll show both again and you decide what you prefer. Method 1 is set up an equation. This is, you want to make sure you get it right. You're decent with algebra 1, at least solving for variables, and this is your method. So set up an equation. What would the equation be? The amount of sulfurs times its charge plus the amount of oxygens times its charge equals to the overall charge of the polyatomic ion. So you're going to have 1 sulfur plus 4 oxygens, that's where these numbers are, S1 and O4, equals to what number? What does all of the charges of sulfur and oxygen have to equal out to? -2. So far, so good?
Yeah.
Now you plug in what you know. Do you know sulfur or do you know oxygen? You're only going to know one of them. You know oxygen. Do you plug in -2 where you see oxygen? Because oxygen is always -2 except for 2 specific situations. This is neither. So you get 1 sulfur plus 4 times -2 equals to -2. Now what?
Will be
1s minus 8 equals -2. Are we good with that? Positive 4 times -2. Signs are opposite, so you get a negative. Okay, go ahead. And how do we end up solving this now for sulfur? Afterwards. So +8 to solve for sulfur. You get S equals -2 plus 8. Are you allowed to use a calculator? Yes, there's no calculator shame. No calculator shame. If you need a calculator for different signs, I'm not your math teacher. I'm not going to get mad at you. Plug it in the calculator. -2 plus 8 is?
S equals
Positive 6. And that's the answer, using method 1. Method 1 is a little bit longer, but it can guarantee you the right answer if you've set up your equation correctly. Let's take a look at method 2. Like I said, you pick which one you want to use. Method 2, you got to pay attention to the thinking process. Let's take a look at method 2. We know oxygen is what number again? -2. So here's what you do. Take -2 and multiply by,
4
which gives you
negative
-8. Now you have to think, what is the number? When I subtract 8 from it, I get -2.
6.
6. Positive 6 specifically. And that gives you the answer. So if this is good for you, if you can do this train of thought, you can solve the questions this way. I have nothing against you solving the questions this way. But if you struggle with this reasoning, then guess what? Method 1 is there for you, which is set up the equation. It's either go through the proper reasoning or set up the equation. But what we care about is you getting the correct answers as you move on. So pick a way to come up with the right answer through either critical thinking or through an algebraic equation. We got more though. I told you there'd be a lot of examples. That was 4. There is more. Yes. After Sarah gets back. There's one in front of you. All right, we're moving forward. What is the oxidation number of each kind of atom in the following? Going on with me. What is that? It is a compound, right? Not an element. Element or compound? It's a compound with 3 elements. What do we do? What do we do? So, anybody have any suggestions? If there's 3 elements, and I'm just going to write this on the side, you will always know 2. If there is 3 elements, you will know the oxidation number of 2 of them. So which one do you think you're going to have to solve for? That's right. You're always going to know the oxidation number of the first element because that's the least electronegative. It's a metal. We know from the periodic table that's going to be +1. We're always going to know the oxidation oxidation number of the last element because that's the most electronegative, and so it takes its negative charge. So we know that this is going to end up having to be positive, right? This is going to end up having to be negative, and chlorine is a big old question mark, right? So if you've got three elements, and yes, this is a scenario that shows up a lot, which is why we have to address it. It is the one in the middle that you'll be solving for. Meaning if you create an equation or if you do your critical thinking, you have to solve for chlorine. Because you know that sodium is the least electronegative, positive charge from the periodic table. Oxygen is the most electronegative, gets negative charge. So let's see if we can figure out chlorine. I'm going to continue using both methods until you, because some of you will be comfortable with method 1 more than method 2, and some of you will be comfortable with method 2 more than method 1. It's just the way it is. So I'm going to use method 1 first. What would my setup be using method 1? How many sodiums do I have? We need the amounts and we need the charges. We know we have 1 sodium. How many chlorines do we have? And we have how many oxygens? And that all adds up to, do you see a number there? Do you see a charge on NaClO3? You do? I don't. 0. It's an ionic compound. The charge is canceled. There is no charge there. There's no number there. We are following rule 5, which is all of the numbers add up to 0 at the end. Now, what can we plug in charges for? Which elements? And what would those numbers be? What would the charge of sodium be? Sodium in a compound is going to be +1 from the periodic table, right? So 1 times +1, which is +1. Do we know chlorine? That's the one I said we were going to be solving for. So we leave that as a variable. You can call it X if you wanted to. If you thought it's really just algebra. That's what you're solving for. And then oxygen. What's the number for oxygen? 3 times -2, right? Equals to 0. So you've got this equation. Solve for chlorine. What will we do next? Okay. So you've got 3 times -2 is?
-6.
So you've got 1 plus Cl minus 6 equals 0. Are you good with Cl minus 5 equals 0? 1 minus 6 is -5. If you're not, get a calculator out and it works. Right. Plus 5 to each side. Chlorine equals +5. Method 1. Those of you that are waiting for method 2 or want to need to be answered with method 2, what would we do? We know this is -2. We know this is +1. -2 times 3 is 6. +1 times 1 is +1. This is your question. All of this has to equal to what number?
0.
What's 1 minus 6? So you have question mark minus 5 equals 0. What does question mark have to be? What does this have to be? Right. +5 because 5 minus 5 equals 0. Check that. Done. That's method 2. Pick which method you're going to use. When you get the homework, pick which method you're going to use. And see if you can apply it with fidelity. Sarah, you're next. F, a reprieve. What is the oxidation number here in F?
It is.
It's an element, right? Is it an ion or is it in its standard state? An ion. What's the charge? What's the oxidation number? Just what it says, what it tells you. That's rule 1. Make a leave out of rule 1. Cl is -1. It's giving you. That's his oxidation number. Telling you that this chlorine has gained an electron. That's what these numbers indicate. How much it's gained or lost an electron. We have 2 more examples. G. BaCl2. Compound. Do we really have much work to do for this one? Just have 2 elements, charges here. Is that an ionic compound? Only 2 elements? What's the ionic charge period? 2. And chlorine? And chlorine? Minus 1. And that's it, right?
Yeah.
If it's only 2 elements, there's not a lot to solve for. If you can pick up the ionic charge, that is the oxidation number. So that's it for that one. It's not a complicated one. One more polyatomic. Oh boy, it's like an H. 3 elements. We practiced one of these. We're just going to practice this one more time. What is the element we're looking for if we've got 3 elements presented to us? We have to be solving for this one. Good so far?
Yeah.
How many of you prefer method 1 so far? Raise your hand if you prefer method 1. How many of you prefer method 2? Raise your hand if you prefer method 2. Honestly, it's half and half. It is literally half and half. So that's why I have to show both. So if you like one method over the other, if you prefer one, just ignore me when I tell you the other. Got it? So go over one and not the other. All right, method 1 for this one. We set up an equation. We've got 3 sodium plus how many phosphorus? Plus how many oxygens? Equal to the overall charge of a neutral compound. There is no charge there, has to be 0. So we add up everything and equal it to 0. Now we plug in what we know, right? The next thing is plug in what you know. Plug in known charges. We're going to know everything except for phosphorus. What do we know sodium has to be in a compound?
+1.
Plus 1. So we do 3 times positive 1 plus P, because that's going to be what we're solving for. And then plus 3 times negative 2. 3 times positive 1 is? Yep. And then 3 times negative 2 is negative 6. You got to be careful with your work here. 3 minus 6 is negative 3. You're allowed a calculator, no shame. And your final answer here using method 1 should be positive 3. Definitely algebra. Method 2. My method 2 people. We're going to do negative 2 for oxygen, right? Negative 2 times 3 is negative 6. Sodium is positive 1. Positive 1 times 3 is positive 3. Phosphorus is your question mark. You have that whole thing and equal to 0. 3 minus 6 is negative 3. You got question mark minus 3 equals 0. What minus 3 is 0? What number would I subtract 3 equals 0? Plus 3, right? So that would be phosphorus plus 3. Same answer, either method. You choose what works best for you. One is less writing. The other one is more writing, but it's clear on how you get the answer.
Yeah.
Wow.
The method 4.
There are advantages and disadvantages to each, actually. Method 1 keeps where we at. Feel like that's the next thing.
This is mentalism.
There's advantages and disadvantages to each. That's why I'm telling you both, and it is an even split typically. It depends. It just depends on the question being asked. All right, so we're gonna cover. Let's see, it's 9 a.m. We're gonna cover at least what is the definition for oxidation and reduction. You don't have to write this down. What's being shown to you here are some common redox reactions. The Statue of Liberty being oxidized by oxygen in the air, and iron being oxidized by rust. Oxygen to form rust. Now, that's where the word oxidation comes from, is that many redox reactions deal with the element oxygen. Oxidation, oxygen. And so, what we're going to be going to, and like I said, I wanted to at least introduce this idea to you. We may not have a lot of time to do many examples today, but I want to at least introduce the idea to you, is how are oxidation and reduction reaction defined in terms of oxidation number. Meaning, we can trace changes in oxidation number to tell us what element has been oxidized and what element has been reduced in a chemical reaction. We're going to define what exactly does that mean in terms of electron transfer. So go ahead and write this question down. I'm giving you a little bit of time. And we're going to go over the definitions for what is oxidation and what is reduction. I told you that was our second goal for the day. The third goal was a stretch goal. Whatever we don't get done today, we have to do next class, because I told you we'd spend 2 lessons going over redox. What we definitely had to understand today is how to get oxidation numbers. That's what you have to understand how to do to be able to move forward. What? I just want to, while I'm waiting, go back to this. I had this going into this compound, right? And we said this happened. Magnesium in its standard state, what would its oxidation number be on the left-hand side? 0. In the product side, when I make the MgO, what does its oxidation number become? And what does that actually tell us? It's going from, it lost 2 electrons, right? This process tells us that Mg lost 2 electrons. So what you're going to be asked to do, and this is what Cambridge asks to do, and actually it's not very much more complicated in the AICE class than it is in the pre-AICE in this specific topic. They're going to ask you to be able to look at this change in oxidation number and say whether this element has lost electrons or gained electrons based on its change in oxidation number. That's really what you're going to be asked to do, which is why I started there. And so we're going to go ahead and do the definitions for oxidation and reduction there on the next slide. I'm giving about 20-second heads up, but I'm moving forward. All right, so how do we know that a transfer of electrons has taken place? An element that has been oxidized, using my example from before, magnesium, has lost electrons on the product side. So going from reactant to product, your element has lost electrons. Are they really lost, or do we know where they went? We know where they went. It's just they don't have them anymore. Like losing my money. You know, I don't really, like, I don't know where it is. I know where it went. Like, it's gone from me and to the casino owners, right? So magnesium in my example I showed you earlier has lost electrons. Therefore, we would say in that process that magnesium has been oxidized. And actually, in the exact example I used, magnesium gained an oxygen. That is definitely an example of that element being oxidized because it's with oxygen. But we've expanded in chemistry past oxygen to incorporate any element on the periodic table. So although the etymology, meaning where the word comes from, it comes from oxygen, because many of these reactions will have to deal with oxygen, it's not all of them. An element that has been reduced by definition has gained electrons from reactants to products. So using my example from before, where oxygen went to oxygen with a -2 charge, we know that oxygen will gain electrons in this process, and therefore we classify oxygen as being reduced. And we are going to stop very shortly. I just wanted to get through the definitions today. We'll be doing the practice of how to trace these oxidation numbers next class. But I want you to see these definitions you're going to need to study because they can be confusing. And this is why. We're literally saying, and I didn't come up with this vocabulary, that an element that has been reduced by definition has gained electrons. How much sense does that sound like? Just read that out. Reduced, like the word reduced means
Smaller now.
smaller. So why is that
chemistry.
the charge is being reduced. So when we say reduced, it's actually the oxidation number or the charge is what is actually being reduced when we gain electrons. And this comes back to that famous idea that can be confusing, that electrons are negative, so everything you think is reversed. So oxidized means lost electrons, reduced means gained electrons, and what actually this means is that in a reduction, the oxidation number is reduced. What does that mean about the oxidation number in an oxidation? Would it be reduced or would it go up? It would go up. So in oxidation, the oxidation number actually, right. I had a student, 2016, they have their master's degree now. They were in the AICE class, and they came up with an acronym. And usually when somebody comes up with a really good acronym, it sticks, and that's fine, use it again. And they memorized it as OMP. What do you think that stands for? Oxidation, more positive. So if you trace your reaction from reactants to products and your number gets more positive, you have an oxidation. And if it's the opposite, then you have a reduction. That's what they used. There will be other acronyms you're going to see next class that will help you. And there's acronyms whenever something is typically confusing. And this is one of the confusing topics. Today, I need you to master how to determine oxidation numbers. Specifically, for elements, for ions, for compounds, including polyatomic ions, either using method 1 or method 2. The final thing I want to bring up is when you answer for oxidation numbers, so I'm going to go back here real quick. When you answer for oxidation numbers, notice how I've written the answer here. The oxidation number is for one of each element. Meaning that oxygen has an oxidation number of -2, not -6. See if that makes sense. Even though all 3 oxygens gain 6 electrons, when we answer an oxidation number, we answer for each individual atom of an element. So each oxygen is -2, each sodium is +1, and each chlorine is +5. That's the way that we answer for oxidation numbers to trace the changes in electrons. So that's something that's really, 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 really important. I'll go back here real quick because I know some of you were writing the definitions down, finishing writing the definitions down. We're going to stop here for sake of time and for sake of the next thing. Need some love. I told you this will be a 2-part lesson. So we will continue how to determine redox reactions. What are the reactions of the 5 we studied that are always redox and never redox? We'll do that next class. Remember, this is only 2 lessons this week. And then on Friday, we're going to practice with a lab. I'm going to pass out the homework. To be clear, because I was not sure how far I would get. Actually, it only printed one-sided. So, yeah. Never mind. You can do everything. There was a back, but there's not a back for you. You can thank the copier this morning or my tiredness. It's only examples A through H. You might be able to finish it before the end of class. If you can, turn it into the period 2 minutes. And double check with me if there's something confusing. It should say N. It should say N. For B, this should say N, not J. Yeah, with the length of time you have and the amount of questions you have, you could totally finish this by the end of class. But that's not me asking you to rush. I'm just saying that it's possible. There you go. There you go. Use either method 1 or method 2. There you go. Practice with either method 1 or method 2. Check with me if you're unsure of your answers, and because you've got about